Here we will start the introduction to aviation and principle of flight. This is a subject where we will learn about the history of flight, major parts of an aircraft, the type of aircraft construction, major flight structures, and basic principles of flight. And now we shall start with the history of flight to see where it all began. Right here we could see our first recorded inventor of flight, who goes by the name Leonardo Da Vinci. He designed the flying machine during the 1500s, but it is deemed impossible to fly such an aircraft due to the requirement of a human powering lift, which is deemed impossible by Robert Hooke in 1655. This resulted in people seeking other ways to soar the skies, which is made possible by Joseph and Etienne Montgolfier in 1783, who made the first manned hot air balloon, which flew approximately 23 minutes. Another balloon was made by Professor Jaques Charles, who made the first gas balloon 10 days after the first manned hot air balloon by the Montgolfier brothers. Meanwhile, a man named Sir George Cayley discovered that kites can be the key to soaring the skies, during which can help with heavier than air flights as early as 1799. He has also discovered the basic principles where modern science and aeronautics were found. Thus, he is crowned as the father of aerial navigation. Sir George Cayley's principles were proven to be practical by Otto Lilienthal, who began testing aircraft heavier than air multiple times, to which it was tested by climbing to a higher ground than to jump and glide using the hang glider, to which became his end when his glider crashed in 1896. And finally, we have the Wright brothers, namely Wilbur Wright and Orville Wright. They managed to build a successful heavier-than-air aircraft by utilizing more engine for powered flight. Said biplane is also named the Flyer, which flew during the afternoon of December 17, 1903 near Kitty Hawk, North Carolina, with a time span of 98 seconds on 4 flights. Up next, we have the aircraft categories. An aircraft is anything that can fly, which are split into multiple parts. We have the lighter than air, glider, airplane, and rotorcrafts. Let's start off with lighter than air aircrafts, which inflate themselves with gases and float in the air. They were the first non-working method used to soar the skies. The primary example of these kinds of aircrafts are balloons, aerostats, and an airship. The next category of aircraft would be a glider, which is a fixed-wing aircraft that does not rely on an engine to fly, but instead takes advantage of the aerodynamic forces using their various controlled surfaces. Those that do have engine power plants are called airplanes. These are heavier than air aircrafts that rely on an engine for thrust and sustained flight. A rotorcraft, or also known as the rotary wing aircraft, relies on rotary wings facing upwards, which rotate at a constant speed to generate lift. This is any aircraft that uses rotors that provide lift. We will now begin with the major parts of an aircraft type known as the airplane. There are a total of 5 major parts that make up an airplane, namely fuselage, wing, empennage, power plant, and landing gear. The fuselage is the main body of the airplane, which houses the crew, passengers, and cargo. This is also where the wings, empennage, landing gear, and power plant are attached to. The cockpit can also be seen within the front of the aircraft, which is the control center of the entire aircraft. The wings are attached to the side of the fuselage and is responsible for the lift that supports the aircraft in flight. They can vary on design, sizes, and shape depending on the manufacturer. They also come in different numbers of sets, such as the monoplane and biplane. Many high-wing airplanes have semi-cantilevers, which are struts that support the stresses of flight, and landing, which are equally distributed on the main fuselage structure. Some planes do not have this, to which are called full cantilevers, which can support the flight and landing loads without the need of struts. A wing has several parts that make up its structure: ribs, spar, skin, and stringers, where ribs determine the shape of the wing. Spars handle the weight of the wing when the aircraft is grounded. Stringers which transfer loads and stresses to equally distribute them. The wing has two control surfaces, namely the ailerons, which are located on the rear outermost regions of the wing that moved in opposite directions, which forces the aircraft to roll, and the flaps, which are located at the rear innermost regions of the wing that extend downwards simultaneously to create a bigger angle of attack on the wing, which can create lift and drag, thus preventing a potential stall. The empennage, which is located on the rear section of the airplane, which include the vertical and horizontal stabilizers, which are fixed surfaces with multiple control surfaces that can help the aircraft pitch or yaw. These control surfaces are as follows: the rudder, which is attached to the back of the vertical stabilizer and is responsible for moving the aircraft's nose left and right. These control surfaces are as follows: the rudder, which is attached to the back of the vertical stabilizer and is responsible for moving the airplane's nose left and right. The elevator, which is attached at the back of the horizontal stabilizer and is responsible for controlling the upward and downward pitch of the airplane during the flight. And finally, the trim tabs, located on the trailing edge of the two previous control surfaces, which are small movable portions responsible for reducing control pressures. The landing gear handles the entire weight of the aircraft when it is grounded, taxiing, taking off, or landing. They can vary with wheels, skis, or floats depending on the location of the aircraft and where it should land. There contain 3 wheels, which has 2 main wheels and the third wheel either located at the front or rear of the airplane, respectively called conventional landing gear and tricycle gear. Finally, the power plant, which provides power to the entire aircraft and the propeller. They are also responsible for the flow of fuel and oil of the aircraft. They consist of 3 parts, mainly the engine itself, the cowling nacelle, which streamlines the flow of air to cool off the engine, and propeller, which generates thrust. The propeller can be mounted on the front as a tractor configuration or pusher configuration. Let us move on to lift and basic aerodynamics. We have the thrust, lift, drag, and weight. Thrust is the forward momentum of the aircraft produced by their engines and propellers. Lift is only produced through the aerodynamic forces acting upon the wing, which opposes the center of gravity and fly upward. Drag is the opposing force of thrust, which pilots take advantage of using through their flaps and ailerons to control their level and orientation of flight. Weight is the combined total mass of the entire aircraft and its cargo under the influence of gravity. We also have the 3 rotational axes that the aircraft depends on to move around during flight. We have the longitudinal axis, which goes along the front to the back of the fuselage through the center of gravity. This is also called the roll axis, which is taken advantage of by the ailerons. We have the lateral axis, which goes along from one wingtip to another through the center of gravity, and this is also called the pitch axis, which can be utilized to pitch up and down to change the Y orientation of the aircraft by using the elevators located on the empennage of the aircraft. And finally, we have the vertical axis, which goes from the top of the aircraft to the bottom through the center of gravity, which can be utilized to turn the plane left and right without rolling. Said turning is utilized by pilots through the rudder located on the vertical stabilizer of the empennage of the aircraft. Now we shall delve into the types of aircraft construction. Aircraft construction has evolved throughout time, for it has evolved from truss structure monocoque structures, and the semi-monocoque structures. We first start with the truss structure. It lacks a streamlined shape which can increase drag and reduce aerodynamic ability. This type of structure is made with longerons that run the length of the framework, struts that equalize the stresses and give shape to the structure, and finally a bulkhead which can help stabilize internal pressure. The monocoque structure heavily relies on the skin to support most of the stresses exhibited by the aircraft. The downside is that it is not tolerant to being deformed, and since the skin carries all the loads and stresses, the need for internal bracings is reduced, which is to be replaced by formers to give shape and structure, while the bulkhead controls pressure within the fuselage. And finally, the semi-monocoque structures, which utilizes stringers to help distribute and reduce the stresses that the skin has to endure. Each stringer is attached to a bulkhead, which is also part of its substructure, which helps strengthen the structure without the need to maximize occupancy of struts. We shall delve into the principles of flight to see what are the fundamental laws that act on the aircraft that causes it to fly, and how said forces would affect the aircraft. First, we start with the atmosphere, which consists of 78% of nitrogen, 21% oxygen, and 1% of the miscellaneous gases, which involves argon and helium. Do note that oxygen is heavier than other gases, which is influenced under the force of gravity. Thus, they settle to the surface of the earth. Also note that air is like a fluid. It will change shape and flow when it is pressured for even a fraction of a second. Pressure is when said air fluid is under the influence of gravity that creates a force that is exerted equally in all directions, which affects any body within the air. The average pressure exerted by the weight of the atmosphere is at around 14.7 pounds per square inch, or 1013.2 millibars. Note that air pressure decreases with increased altitude, and that pressure is measured by a mercury barometer. Meanwhile, standard atmosphere at sea level has the surface temperature of 59 degrees Fahrenheit or 15 degrees Celsius, and a surface pressure of 29.92 mercury. Now, we shall note that the atmospheric density depends entirely on the altitude. Where altitude increases, pressure, density, and temperature decreases, and that atmospheric density is vital to aeronautics as the power plants and engines heavily rely on the atmospheric density to create thrust and lift for the plane to fly. We can also state that the atmospheric density is at around 1.225 kilograms over meter cube for 101.325 kilopascals at 15 degrees. We shall start with the theories in the production of lift. We are currently focused on two of the major theories about the production of lift, Newton's theory and Bernoulli's theory. We shall start with the Newton's theory of lift, which involves the basic laws of motion, where the first law states, and I quote, "Every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it." We can set an example for this. To when an aircraft is stationary, it is at rest, but once the engines begin pushing the plane, it is compelled to change from the state of rest to a state of forward momentum. His second law states, and I quote, "Force is equal to the change and momentum per change in time. For constant mass, force equals mass times acceleration." We can state that an aircraft moving at a given speed has enough force to move the entire weight of the aircraft. And finally, Newton's third law, which states, and I quote, "For every action, there is an equal and opposite reaction." This holds true to the nature of the power plant of the aircraft, where it pushes air back at high speeds that pushes the plane forward. Now we move on to the next theory, which is named the Bernoulli's principle of differential pressure. And this states that when the airplane is at a constant speed, the airfoils create a low pressure area that originates from the upper surface of the wing. That, along with the high pressure area that originates from the bottom of the wing, shall push the wing upward, thus creating lift. When air strikes the lower flat surface of the wing, it is forced downwards by the angle, which in turn causes a counterforce that pushes the plane upward, while some of them go towards the upper curved section of the airfoil, which causes a reaction when the air is rebounded downwards which in Newton's law provides an equal reaction, forcing the airfoil upwards. To support Bernoulli's theory, we shall proceed with the airfoil design. We can note that the airfoils resemble a teardrop design. This happens to be able to create a desired pressure required to create lift. Now we can extend on these parts. First, we have the leading edge. It is self-explanatory, which is located on the most forward region of the airfoil and the mean camber line. The mean camber line, which is the region that is equidistant from the top and bottom of the airfoil. The chord line, which is a straight line connecting the leading edge, trailing edge. And finally, the trailing edge, which is located at the most rearward point of the airfoil and the mean camber line. Okay, my fellow viewers, that is all for today. I hope you have learned something from this educational video, and I will see you next time. Nathaniel B. Juguilon of 20, Bachelor of Science Aeronautical Engineering 1A,